of designing the processor. If you remember, in the last class, we were talking about the instruction fetch section. So in the instruction fetch section, we saw that there was a component which is actually known as instruction address generator, and we have seen that how the instruction address generator is basically connected. So if you look into the diagram that in the last class which I was talking about, let me share my screen. So this one we were talking about, this particular circuit. So instruction address generator. I have already uploaded all the hand notes in the lecture notes section of the Microsoft Team class. You can actually look into this. So this instruction address generator is the unit that is responsible for getting the next address or getting the address of the next instruction to be fetched. Okay, let us see that how we can design the circuit for instruction address generator. Again, it's not a gate level circuit, it will be a block level circuit. Let us first investigate that. So we will talk about instruction address generator. So a typical circuit for the same looks like this. Let me first draw the circuit and then I shall explain that why this can be a solution. So this can be an implementation of the instruction address generator. Let us see that how the same circuit can be used for generating the address. Okay. Now, let us take some examples first. So your first instruction is, say, for example, move R1, comma R2. Next instruction is, say, add R1, comma R3, comma R4. Then another one is, say, let's say jump or rather I'll say branch, because branch is the branch if R1 equals to R2, then offset, else it will be, say, move R2, comma R3. So don't try to find any meaning of this code. They may not be doing any operation. I just randomly wrote these things. Just a second. So don't try to find any meaning of that, what are the sequence, but let's assume that the PC is currently pointing to this. Okay. So currently the program counter value is pointing to this. So when this particular instruction is getting executed, that means its fetch is already over. Okay. So the value of PC is here, and by the time when the instruction gets executed or decoded, the processor understands that this is not a jump instruction. Okay. After decoding. Now, if you look into the operations that will be performed during the fetch stage, you will see that without actually looking into the instruction, it automatically increments the program counter value by 4, by default 4. Okay, so that the PC points to the next. When this instruction is getting fetched, the same value is being used here to point to the next instruction. That is a typical procedure. Okay. So the value of PC comes here. When this instruction is getting fetched, the same value of PC comes here. This goes to the adder, and on the other side of the adder, there are two options. Multiplexer INC, it either passes through 4 or passes through an immediate value. But because this is a fetch stage, it doesn't know that whether what is the type of the instruction. It's simply the multiplexer select line, the control signal generated here. This control signal during the fetch stage of move instruction. So it automatically selects this 4. Okay. So the value of PC gets incremented and it comes here. Again, gets loaded. Okay. And at the same time, when this control signal during the fetch stage of move, okay, it passes at the same time synchronously this signal also selects this one. So the updated value of the PC is stored here. So here basically what happens, PC equals to PC plus 4. It's a normal operation when this one to this one is happening. Similarly, when this one to this one is happening, again PC equals to PC plus 4 happens. Whereas at the second stage, when a particular instruction gets decoded and when the control unit understands that the previous calculation of the program counter, which is PC equals to PC plus 4, needs to be updated due to branch instruction, which happens here itself, what it does, it again does the same selection line high at the decode stage. But during that time, the other side of the selection line goes high, or the control signal which is generated now selects the other point. So if you make it 0, if it is 1, so now 1 is selected. So PC equals to PC plus 4 plus your branch offset is calculated, subject to the condition that if R1 equals to R2 is satisfied. Now the question is that whether this will be done at the decode stage or execute stage. We can discuss it at later stage. Let's assume that it is done, it is resolved at the decode stage, but it is very difficult to resolve at the decode stage. It has to be only understood at the arithmetic logic stage, because this comparison R1 equals to R2 will be done at the arithmetic logic stage, ALU stage. For the simplicity, we can assume that there is a way to know that during decode stage. So again, during the decode stage, the same multiplexer gets activated, but this time the value comes from here, and the offset value, which is already given here, that comes through this line and it gets added with the PC equals to PC plus 4, and again this line selected, say this is 0 and this is 1, and the new PC value is loaded subject to the condition that R1 equals to R2. Okay. So we understood that how this particular function, particular part actually works. Now let us see into this part, left side of the circuit. In the left side of the circuit, if you look into it, every time the value of the PC actually gets stored into a temporary register PC temp. This is just for the reason the return address. So return address is nothing but the address where, now let's assume that you have a return, you have an instruction call location. Now your PC value is currently here. Now what you expect after the subroutine is executed, so that subroutine execution will be done through this offset value. Okay, because this is an offset, location is nothing but offset from the current location. But you need to remember the value PC equals to PC plus 4. So that's why this first time when the value of, because by the time you understand that this is a call, PC equals to PC plus 4 has already been done. So that value gets stored here. Always it is stored here. And this actually goes to multiplexer Y. Now if you remember in the earlier diagrams where I actually I have shown the complete pipeline where basically we have looked into it that in the multiplexer Y there were 3 lines. In marks Y there were 3 lines. One line was directly coming from RZ, other was coming from data, memory data, and another one was return address. That is basically nothing but PC temp. So this value now goes to through multiplexer Y, and the multiplexer Y gets selected, and where it will be stored? It will be stored here. Next time, where from you will get the PC? So when the now this is basically when you find a call, when you find a call instruction, this part gets activated, and it is passing through multiplexer Y. Where it will go from multiplexer Y? Can someone tell me where it will go from multiplexer?
Registers.
Yes, it will go to register file. It will go to register file RF. So it may go to a designated register, return address. That's why there may be a specific register where it will go. Now come to the, so when it is called inside the subroutine, now this is the subroutine. So at the last, what is the instruction? Return. So when the return comes in the subroutine, the value actually comes from, so this multiplexer marks PC selects the value from the return address, which was stored in a register file. So that value then comes. Okay. So the return address, which is stored actually in a register file, that value comes as a return address, goes through multiplexer PC. This time it will not select the next address after return. It will rather select the value which is coming from here. So the select line will be activated 0. Now the 0 activation will come when the instruction is returned. Okay, so now you probably understand that why. So this is for the return part, this is for the call part, and this is usually the address calculation during branch and call. This is the saving the address. This is calling to the new address or branch. This is usual PC equals to PC plus 4. Is that clear to all? Why there is so silence? Is it clear to all of you that how this particular circuit works?
Sir, PC temp will always store values, and we take mux y values. It depends, right?
Yeah, it depends. It depends.
Okay.
PC temp will always store the value, but whether it will be used by the multiplexer or not, that depends that what is the current instruction. If it is a call instruction, then only it will be taken from here.
Okay, sir.
Similarly, this marks PC, RA value will come here always. Whether it will be taken or not, it will be decided whether it is a return instruction or not. With this, can I solve nested call? I now raise a question to the entire class that with this same function, can I implement nested call? If I want to implement, what kind of modification is needed, and where is the modification you require?
Sir, two modifications we can do, I think.
Tell me.
Sir, in PC temp, like we are always using like mux y, we should choose. Yeah, yes, sir. Return at means C address of register file we can choose accordingly in a stack wise manner, and RA should be chosen accordingly. Like yes, sir, we can do it.
So that means you need to change the return
Addresses of
address register, implement it using a stack.
yes, sir.
Yes. So you need to modify that portion of the register file where you are storing the return address. It cannot be a simple register then.
Or sir, we should do like one control unit formation for like if we are doing for these calls, like separate file we can make like few registers for calling only.
Right. So that's why you can understand, if you really want to implement the nested subroutine, okay, using a hardware scheme, you can now understand that there will be difficulties. That's why even if you write nested subroutine in your program, in your high level program, when the compiler actually optimizes it, compiler tries to serialize it. Otherwise, you need a lot of dependency in the hardware part, which may not be feasible, like implementing a stack to get the top register value where the return address is stored itself is a challenging thing. Okay, or you require additional hardware for that. On top of it, how many elements will be there on top of the stack or in the stack? You cannot have infinite number of elements in the stack, particularly in a register organization. But your nested loop can go any level. Calling one function, you think about towers of Hanoi or those programs, recursions, typically where we call one function inside another one, this way it goes on. So since we don't put any restriction on the input size, when we provide solution, hardware solution, we must take care about that whether the hardware solution is capable of handling any data, because we do not want to put any restriction on the size of the data, input data. You say that you will implement a stack with 4 registers, 6 registers, 8 registers, but can you guarantee that all programs written by any user will be satisfied? No, you cannot guarantee. So that's why you have a hardware limitation. You cannot keep on adding registers. That will unnecessarily increase the cost of the processor as well as the complexity. So this sort of problem is usually handled at the software level. Even if it may provide maybe 4 levels of nested calling, but beyond that it will be difficult. 4, 8, I mean to say that you can decide, but there has to be some limit. Okay. So now, keeping in mind the whole 5-stage pipeline, let us try to examine the steps needed for executing the instructions. So steps for fetching and executing the instructions. We need to now write down in terms of register transfer notation. Okay. So we'll start with an instruction, say add R1, comma, R2, comma, R3. So obviously we'll have to encode the instruction. So encoding of the instruction, we know that this is a 32-bit instruction. You can encode it depending on how many functions you are going to implement it. Okay, so encoding part I will come later stage, particular to the RISC instruction, how the instructions are encoded, we will see later stage. But let's assume that the encoding is done already. Now for this instruction, I would like to find out the steps with the same 5-stage pipeline. So 5-stage architecture. So we will use this 5-stage architecture that we have already seen. And we want to make the steps stage wise. So we'll have step, then action. Step number 1. What we can write? So there is a register, memory address, which holds the memory address temporarily. This register gets the value of program counter. What you do then? You apply a control signal that is called read memory. What you expect? Your instruction register will be filled with memory data. At the same time, what you do, PC equals to PC plus 4. So these are the 4 steps which are done during the fetch stage. So this is instruction fetch. What you do? The value of the program counter is placed on the address bus, or you can also store it in a memory address register. The control unit generates a read signal. After some time, the data is available in memory data, which is placed into a register, instruction register IR. During that time, the program counter value is incremented with the circuit that I was earlier discussing. I was showing the program counter value is incremented by 4. So these are the 4 steps. There are other small steps, but these are 4 important steps which are completed during the first stage or the instruction fetch cycle. And this is common for all instructions. That's why I can put as asterisk mark. So this is mandatory step. This is mandatory step. You will not find any change into this step. This will always happen. So what will be my second stage?
Sir? Sir, memory address is that RM register which you showed in that last class.
Memory address is the
RM register which is going to which is providing memory address bus to data.
No, memory RM is the data register. RM is the data register. Okay, it is basically for storing. Okay, so memory address
is a temporary register which is holding address.
Yes, there is a temporary register which is holding address, which may be required, or it can directly place the address on the address bus itself.
Okay.
Now, the next stage, which is the decode stage. So what it will do? It will basically decode the instruction. So where is the instruction? It is in the instruction register, IR. IR holds the instruction register. The opcode and other part of the instruction is already loaded into instruction register. So now that gets decoded. As per this particular, now it will be specific to this instruction. What will happen? Add R1, R2, R3. So what do you expect? Because decode stage, you not only decode, you also read the operands. This is operand read cycle. So what you would do here? Can you tell me that what will be the register transfer notation here? For this instruction? Any guess? So this is destination, this is source 1, this is source 2. So in the yes.
R2 and R3 we will bring.
Where? Memory.
Okay.
You remember the 5-stage pipeline? That 5-stage pipeline that I have already discussed. All the interstage registers I have already mentioned in the diagram. With respect to that, you'll have to tell.
RA and RB में आएगा.
Right. So RA will be this one. RB will be this one. So the content of R2 will come to RA, content of R3 will come to RB. So this is my decode stage. Decode and operand read stage. Third is arithmetic logic stage. With respect to this, what will happen? Remember again the 5-stage pipeline?
RA plus RB will go to RZ.
Yes, so RZ equals to RA plus RB. That's very simple. In this particular instruction, it is simple. So this is my ALU stage, or you can say execute stage. Fourth stage, it's memory. But we do not have any memory operation for this particular instruction. So what it will do? It will simply pass the value from RY to RZ to RY. Again, go back to the diagram. So you will find that it will simply do like this. So the value which is stored into RZ after the addition is transferred to RY. You can understand that during this transfer, what will be the control signal for the multiplexer Y? So this transfer only ensures that. What this transfer means? Generating the multiplexer signal appropriately. So that RZ line will be selected and it will be passed through the multiplexer and it will go to RY. That's it. So this is the memory stage. Even though it doesn't involve any kind of memory, it just passes the value. So the data line, address line, they are now inactive. Inactive means the outputs, the value which is stored into RY comes from directly from RZ. Accordingly, multiplexer Y line gets selected. Fifth stage. Yes.
RY goes to RC.
RY goes to?
RY goes to R1.
Yes. So R1 is RY. This is right back. So this is what happens when add R1, R2, R3 instruction goes through the 5-stage pipeline and the circuit that I have already, block diagram I have already discussed, and how the steps can be written using register transfer notations. This is like this, where we will see that for other, I have just shown you one instruction. I will take other instruction and I'll show you that how the same pipeline can be used for executing other instructions. Is that clear? These steps which logically we actually found based on that architecture. Is that clear to all of you? It's good that seems to be clear now. Let us take another example. Move R1, R2. This one will be common, as I already told you. Memory address, PC, read, IR, then PC plus 4. This is common, we have already seen. Second step, decode is common, decode instruction. Then what will happen?
We'll load into RA.
Which one? R2 you will load it into RA, huh?
Source this.
So RA equals to R2, huh?
Yes, sir.
One minute. Okay. Just hold on, I need to take this call. So RA equals to R2. Now, what will happen after that?
ALU will bypass it.
How you will bypass ALU?
Sir, there are two options. Either we can load means if like you said in one of registers that one.
Hello.
And give immediate. So two options are there. One either one particular register we can set it at 0 and load it into RB and perform addition, or another option can be immediate value we can give at 0 and perform addition.
But immediate 0, where from you will get it? Immediate value is directly coming from the instruction field.
Okay, sir. So we can
immediate value is connected with the instruction offset field only, directly connected. So here actually we need a modification in the circuit. That modification is simple, that the value of, if you look into the diagram where let me show you the diagram. Let me show you the diagram. Is my screen visible?
Yes, sir.
Now look into this diagram. So this is the 5-stage diagram that we have already discussed about. So the value comes to RA. From RA it goes to arithmetic logic unit, and from arithmetic logic unit it goes to RZ. So what probably we need to do is introduce a multiplexer here at the input of the RZ. Either it will take the value from arithmetic logic unit, or it will take the value directly from RA. If I do this simple modification, I will add a multiplexer here, and the output of the multiplexer will be given to RZ. One of the inputs will be from ALU, another input will be taken from the RA. So that will bypass the arithmetic logic unit. Right? Do you agree with me? So what I do? I'll do the modification like this. This is RA. And this is arithmetic logic unit. This is RA. This is arithmetic logic unit. What I will do, before I give it to RZ, I will pass this through a multiplexer. I can do it, right?
Yes.
Yes. This is one solution. The other one, like probably Sushant was suggesting, that you can actually give an immediate value here, this line, which is 0. That is also possible. What you can do is usually what happens, this multiplexer has 2 lines. One is RB, another one is immediate. This is from instruction. You can also give another immediate value 0. This is max B. So to bypass this, you can use this one also. So this multiplexer will select either RB or immediate value from the instruction or 0. And then there will be an add instruction, so that RA plus 0 equals to RA, and this, so you can avoid this multiplexer. So both are possible. Is that clear now? So how? So we are improvising the design now, depending on the requirement. Is that clear to all of you? Class is today very silent. Let me see that. How many of you are present? I'll do a roll call now. Let me check it. How many of you are present? I feel that many of you are not present. 16 batch 1022 present. Chandra Prasad.
Present, sir.
1036 Jitin. 1038 Satya Supriya. 18 batch.
Present, sir. Present.
1048 Sudhanshu Kumar. 18 batch. 18 batch 1049 Venkat Sai. Tarun. Now coming to 19 batch. Tarun. Aviram. Nihant.
Present, sir.
Bharat Mishra.
Present, sir.
Akhil.
Present, sir.
Pavan Kumar. Arpit.
Present, sir.
Anudeep.
Present, sir.
Sujit. Nitish Kumar Bora.
Present, sir.
Rohit Reddy.
Present, sir.
Navneet. Sukrit.
Yes, sir. Present.
Kushagra. Vijay Ketan.
Hello, sir. I'm Navneet, sir. I just logged out of the call to join from laptop, sir. I was
Okay.
there till 3 minutes back.
Okay. Venkat.
Yes, sir. Present, sir.
Jyoti Kiran Reddy.
Present, sir.
Divyans. Divyans Agarwal. Rahul Pathak.
Yes, sir.
Atul. Avinav.
Sir,
Atul.
sir,
Present, sir. Present, sir.
Who is speaking?
sir, this is Sir Kushagra Gupta, sir. Sir,
Where you were? I. Are you joining now?
sir. No, sir,
Why are you
sir. I
joining
have
now? Why you are not there since beginning? Your friends are saying that sir is taking attendance. All of you join. It should not be like that. Atul. Udit.
Present, sir.
Shahidi. Shahidi. Niharika.
Present, sir.
Shravani.
Present, sir.
Janvi Sri Sai. Bharat Kumar Reddy.
Present, sir.
Parth. Ashok. Sri Vidya, Sai Giri Nandini, Adesh,
Present, sir.
Prabhatala Teja, Anand Amar,
Present, sir.
Dheeraj, Aviram, Vikas,
Present, sir.
Vamsi Krishna, Saket,
Present, sir.
Nikhil Kumar,
Yes, sir. Present, sir.
Anirudh,
Present, sir.
Ashwin Kumar,
Present, sir.
Santosh,
Present, sir.
Sindhu, Akshay,
Present, sir.
Pranaya,
Present, sir.
Abhijit,
Present, sir.
Pavan Kumar,
Present, sir.
Praveen Kumar Rao, Satvik,
Sir, Satvik here, sir.
okay, Monish,
Sir, present, sir.
Manoj,
Manoj, present, sir.
Vineet, Vineet Babu,
Present, sir.
Vamsi, Gaddu Vamsi,
Present, sir. Vamsi.
Jyoti Priya,
Present, sir.
Dinesh Nayak,
Present, sir.
Dhruv,
Present, sir.
Kishore Kumar, Vinayak, Moksha Vinayak, Moksha Vinayak, Sujatha,
Present, sir.
Tapeti Mohan, Lapeti Mohan,
Present, sir.
okay, Harsh Singh Jadon,
Present, sir.
Sangram Misra,
Present, sir.
Jagdish,
Present, sir.
Yogesh, Prashant,
Present, sir.
Sai Krishna,
Present, sir.
Dhiren, Sarthak Gupta, Harshavardhan, Rohan Harshavardhan, Deepti Sai, Kaushik Kumar,
Present, sir.
Durga Prasad, Agam Yadav,
Present, sir.
Likhita,
Present, sir.
Anuj Manoj Kumar, Harshit,
Present, sir.
and Sushant.
Present, sir.
Sir, this is Dhiren. Was I audible?
Who is there?
Dhiren, sir, Dhiren.
Tell me your roll number.
2002, sir. 19 CS.
2002, Dhiren. Okay.
Sir, this is part CS28. I was muted, so yeah, not able to.
37, Vamsi Krishna. Nine.
CS28 part.
Is Mark.
Present, sir.
Who is there? Sindhu. Why people are now responding? Earlier you were not there.
So I was muted, kind of.
Muted kind of. What is your roll number?
CS28.
28. Okay, 28 I have given. Parth Ashok.
Sir.
Ah.
Sir, 16 CS 36. Sir. Jitin.
Where
Sir.
you were?
Sir, I was on, sir. Actually, I had class since 8 o'clock, sir. My net is very slow.
You were sleeping, that means.
Sir?
I mean to say that you were you sleeping when I was calling your name?
No, sir.
So why you have not responded? I remember that I pronounced your name 2-3 times. ठीक है, चलो दे दिया.
Sir, actually I had class since 8 o'clock, sir. 2 hours class before. My net
8
is
o'clock.
very slow.
8 o'clock since which class?
Compiler design lab I had. Sir.
Okay.
That's why, sir, actually. My net got slow due to labs.
Okay, ठीक है.
Thank you, sir. So okay. So let's come back to our discussion. So now you understand that why I told you that the modifications we can do it depending on what is your wish. Probably the hardware requirements may vary depending on where you are applying, but these modifications are well possible for a simple modification. Now, as I already told you, you need to understand the concept, because in the examinations you will expect questions like this, not a direct question. That's why it's very important you attend the classes. Okay, I will not ask you straight away that design the 5-stage pipeline and tell me that how it works. I will definitely ask for something which is new. So if you understand the concept, it will be very easy for you to answer. If you don't understand, then it will be very difficult. Okay, so that's why it is very important you attend the class. Okay, earlier I did not take attendance. I just copied it from your attendance values which are coming from ERP or Microsoft Team. But I feel that many of you are not responding. So this is not good actually. If you do not listen during the class time, you can always listen to the lecture, recorded lecture, but that will not give a feeling. If you have any doubts, you can immediately ask me. So that's the advantage of attending a live class. Okay. So we will move now to the next part of the discussion, that how do we basically, so this is the second stage. What will be the third stage? Can someone tell me? So in the second stage, you do it decode instruction. Let's assume that I use a bypass path like this. What will be the third stage?
No third stage then, because it's a
Why not?
RZ to RY.
No, third stage.
RZ, RA goes to RZ.
Yes, RZ equals to RA. That has to be done, no?
Yes.
Yes, either you do this path or that path. It has to be done. Okay, if you take it this one, then you'll have to do the addition and then do it. Otherwise, or RZ equals to RA plus 0. One of them has to be done. So if you take this path, then this. If you take this one, then this. Correct? What about the fourth stage?
RZ to RY.
Yes. So RY equals to RZ. Fifth stage, R1 equals
Load
to
at R1.
R1.
Write that R.
R1 equals to R1. So now probably you understand that how this instruction move R1 comma R2 gets executed through the pipeline. Okay. Let me take another one example. This time I want your answers. I will not write down anything. Let me see that how you are following my lecture. Let's take the example of this. So this is 4th page. I have an instruction like this. Load, say R3 comma X R4. Now this is my step. These are my actions. Number 1 is common. I'm not writing. That we know it. We have already copied it from the first one. Tell me the second stage.
First decode.
Equal to R.
One by one. Decode. Okay, decode. Instruction. Then?
Load X and R1.
No, tell me in terms of RTN.
RA में X, RA में R4 और RB में X.
RA will get?
R3, R4.
RA will get R4. Okay. Then?
और RB में X.
RB में what?
X.
Why X will come in RB? Look into the diagram.
It will
Immediate
come
value
as
में से
immediate.
जाएगा, not RB.
Look into the diagram. Where from X is coming?
Immediate
X
value.
is
Immediate value.
So RB is above that. So nothing will be there in case of RB.
Okay. Yes.
It's nothing. So what is the third stage?
Add both of
Z
them.
equal to RA plus X.
Tell me in terms of RTN.
So RZ takes RA plus X.
RZ is equal
RZ
to
equals
plus
to RA plus immediate value, huh?
yes.
Which is X. Fourth stage.
RY equal to RZ again.
No. Remember, this is load instruction. I want the correct answer from these 3 steps. Here are 3 operations.
Right.
One
So
by
memory, yeah. RZ goes to memory address and memory data comes.
So memory address equals to RZ. Good. Then you have given the address. What is this operation?
Mux
Load.
Y equal to 1 takes memory data.
It will be loaded in RM.
Before you do it, what you need to give an instruction to the memory? This is an address. You have generated the address. You gave the address to the memory. What
Read.
else? Read signal. So you give read memory signal. And then you get it a value. Where it will be there?
In RM. No. It will be from mux. We need
Mux
to.
y. Mux y.
So that means not mux y. We will not say mux y. So what will be the RTN? RY. RY will be memory data. Got it? Fifth stage. Fifth stage.
Load into RF.
Tell me RTN. For this instruction, tell me what is the RTN, register
RY
transfer.
goes to R3.
Yes, R3. R3 goes to RY. Correct?
Yes.
And this first one is common. What about this? If I make it like this, store, sorry. Say if I give it store R3, comma, X, R4, the same. I just change this. This is common. What will be the second stage? Decode. After that, tell me what will happen.
R4 will go to RA. R4 will go to RA.
R4 will go to RA. Okay, great. RA equals to R4. Then
Immediate value plus RA.
you do not need to read R3.
So RB takes R3.
Yes. RB takes R3. Third, RZ equals to RA plus immediate value. Anything else to be done in this stage?
RM takes RB.
Yes, RM takes RB. So the data goes here, address gets here. So now your address is ready, data is also ready. The fourth stage is
Store memory signal.
memory address equals to, first you need to give the value. This is address, then memory data equals to RM, then write memory, what about the fifth stage? No action, nothing is required. Is that clear now? Store, how the store happens?
Yes, sir.
Sir,
So no action means what? Mux Y will be disabled.
Yes, there will be no signal generated for mux Y. That's it. It will be disabled. No value will pass through mux Y. That's it. Now I am taking an instruction which is, say, a branch instruction, conditional branch instruction. Let's take an instruction like this. Branch if, say, R1 equals to R2, then loop. This is the instruction. The instruction is this. What will be the second step? Decode, then?
Sir, can you move down the paper a bit? The instruction is not visible.
What will be the second step?
Can you read the instruction once?
Branch if R1 equals to R2, loop.
We will load R1 into RA and R2 into RB.
Yes. So we'll load RA equals to R1 and RB equals to R2. Third stage.
Use ALU for comparison.
Yes, so compare RA to RB, and if RA equals to RB, then PC equals to PC plus loop. Loop is an offset. Assume that loop is an offset. PC has already been incremented by 4. You can understand. So accordingly, the branch offset is set. Okay. Because in the first step, PC has already been incremented by PC plus 4. So actually, this loop means current instruction plus next instruction plus offset. Current instruction plus 4 plus offset. That you'll have to remember. So this offset, when the user gives, it has to be accordingly given, not from this location. Actually, this from the next location. Offset. During this time, the other part of the circuit, the instruction address generator, will be activated. PC equals to PC plus loop. What about the fourth stage?
No need.
No action. Fifth stage, no action.
So return address or something of the sort to be taken in RY is.
Where is the return address here? This is branch.
Okay.
This is a branch instruction. If it's an if else statement kind of thing. If condition, then go. There is nothing like return here.
Sir, offsets can be negative.
No. It should be positive. Whatever the value is there, it is taken as a positive.
But like in our assembly code, if
16-bit
we write,
values, that's why I got it. You are saying that when it basically comes to the previous location, no?
yes, sir.
Some processors, they do not support it. Okay, the backward jump. Some processors support. It is design specific. Usually they don't support it. So all these backward jumps act. That's why they are expanded and they are dealt by the compiler itself, so that always it becomes forward jump.
Okay.
So after compilation and code optimization, the original size of the assembly code even gets larger because some portion needs to be copied again. It is not necessary that the size of the code will decrease always. Is that clear? Branch if R1 equals to
Yes,
R2.
sir.
Look. Okay. I am giving you an assignment right now. Take your pen and paper. Do this for me. Okay. The instruction is, I will not write, you do it. Don't consult any book on anything. Just try by yourself. Do this. Call register say R9. This is the instruction. What it does, calls the subroutine whose address is given in R9. Write the steps. Logically think about what can be the possible steps. Show me the actions.
So R9 contains memory location or it? Okay.
It's already written, na? The address is given in R9. Okay, I got one answer. Let me see other answers also. Other than Sushant, anyone else? I've got two solutions, Jagdish and Sushant solution. Only two. So Sushant has given this solution. Let me share with you.
So first step is common as before. You are saying that decode, then RA is your R9, right? Oh, what happened? RA equals to R9, then PC equals to RA. You are saying PC equals to RA. What about the value of storing the PC value into the temp?
PC value is always stored in temp, right?
Yes, so that transfer you'll have to do it now. The transfer, it goes to the temp. It's not always. You'll have to do the transfer.
Sir, PC is always initialized with PC temp is always initialized with PC, right?
No, it's not always. Even if it is always, you'll have to do the transfer, no?
Yes, sir. In the next stage, we bring PC I have initialized with RA, and in the next stage, via return path of must-be, I am initializing.
No, what I'm saying that if you look into this part, the PC value of this PC value goes to PC temp. This transfer you'll have to do it, no?
Oh, I thought it is happening automatically always.
No. You'll have to do the transfer. This PC goes to PC temp.
Okay, sir.
This transfer has to be there. So PC equals to PC temp, then the RA value goes to PC, and then PC temps to RY, and RY goes to return address. Yes. So RY go to register link. There is a link register actually. RY, you can write it return address or link register. That's fine. Both are, same. Good. So let us see that what Jagdish has given. वो डाटी writing है. Decode RA R9. Okay. What is this?
The IAG steps I have written other in afterwards. They will happen while step 3 and step 4.
Achha, IAG means third stage.
Yes, because that circuitry was 5-stage circuit was different and this instruction address was different. So.
ठीक है. So PC temp equals to PC equals to RA. Yes, RY equals to, this is a register actually, link register, return register or link register. This question mark you can replace it. This return address is not RY. This is PC equals, basically PC equals to PC temp equals to RY, na?
Sir, from the perspective
PC
of the
temp
other circuit,
return address.
PC equal, return address. This return address is
that 5-stage circuit's return address.
Yes, that's fine. 5 stage. So basically this return address comes, this return address is basically coming from the PC temp value, na? RY.
Yes, sir. PC temp goes return address, one more step we can run in IAG.
Okay, so this one has to be PC temp to RY, then RY to link register or return register. Okay.
इसमें PC temp इसलिए नहीं लिखा क्योंकि PC temp आपने बोला था एक रजिस्टर है करके, तो मतलब डायरेक्ट वायर भी ले सकते थे वहां से.
No, it's a register actually. It's a register actually. This transfer has to be done. It is not an automatic transfer. From
तो
here to here, it's
नहीं कर सकते. मतलब बस से नहीं कर सकते. We cannot do it by bus.
No, you cannot do it. You have to store it in temporary location. Okay, I mean to say that you got the idea that how to do it now. Okay, so that's good that you people probably trying to connect these things, that how it is working. So hopefully you shall be able to do for
other instructions, like if I give something like this, say return, simple instruction is return. And also you can have an instruction which is like unconditional jump. Okay, if the instruction is unconditional jump, what will happen? So that you can write it. I have not written it, but unconditional branch. Which is equivalent to jump or go to, simple go to. So do these two by yourself. Okay, I hope that you will be able to do this. So that's it. Today I will finish it here itself. And हाँ बोलो.
जब RY आ जाता है from PC temp, then what happens to RY again? उसके बाद
जब RY आ जाता है PC temp पे, PC temp
से आ जाता है, then what happens उसके बाद? Fifth step.
It goes to the return register, na, link register.
Means it goes to register file.
It goes to register file. You'll have to store it. You are talking about call register, na?
हाँ.
So call means you'll have to save the value, na? Next address you'll have to save it. ठीक है? So saving कहाँ पे होगा? Saving will be
register file
in a special register. So you can call it link register. Okay. A return register, there is a designated register. It should not be in a particular register R1 to R3 or something like that. It is basically a special register which will be automatically fetched when the return instruction will be executed. So that's a designated register. That's why I'm talking about. If you do nested call, then how many such registers you will keep in the register file? There is a limit. So the value of RY from RY, it goes to a return register. Okay. So the return register is a single register. But if you have nested call, what will happen? So that's why I asked you that how do you basically solve this? Like someone, I think Sushant was suggesting that you will implement a stack kind of thing there. That's a solution. Instead of having a single register, return register, you can have an implemented stack. Is that clear?
Yes, sir.
Sir, our operating system Viva will be new.
I'll schedule it. Maybe I was about to. Today I am busy a little bit. I have some meetings in the second half. Tomorrow, what is the schedule? I will do maybe another 20 students tomorrow. Sometimes if I find second half. So let me. What is your class schedule?
In the morning itself.
Second half, you have any classes?
Half day, sir.
Tomorrow half day, na? So then tomorrow second half I will email. So don't worry. So maybe tomorrow second half I will take some students by one. Okay. I'll mention that roll number from which roll number to what roll number. Maybe not because I have only completed up to roll number 30. I understand. So maybe up to 50 I will take it, not beyond that. Then next lab I will take it.
And in the COA lab, you will take Viva, right?
Yes, COA I'll be taking tomorrow, day after tomorrow. COA I may start little early because I have another one talk from 5 o'clock onwards. So I'll be starting the COA lab maybe little early from 2 p.m. onwards. Okay.
Sir, can you please mail like which roll number you will take so that like my roll number is ultimate last. So.
So wait, don't worry. I know that your roll number is the last one. So the point is there are 3-4 assignments in the computer architecture. I need to, obviously not more than 30 students I can take it. Okay, so anyway yours will be some other date. 30, 40, it's not more than 40 I can take. Okay, even if I do it very quickly.
And sir, for midsem, where should be the practice questions?
There is nothing like practice question. Okay, you will have to follow the lectures. Okay, and all questions will be from the lectures part what I have discussed itself, but it will not be direct one. Like I have given enough examples today that how do I want you to think about a new design. Okay, so it's very difficult to find out questions, particularly in my subjects. You will not find anywhere because I generate questions every time. Okay, separately, you will not find it anywhere. So it's better to understand the concept, and if the concepts are clear, you will be able to answer. I'm pretty sure that you will be able to answer.
Will we at least get a starting premise or starting circuit in such type of questions?
Yes, everything will be mentioned. If I want you to do a modification, I will tell you what is the circuit and you do the modification then. Let's assume that if I ask you to do something, then I will tell you, okay, let's assume that this is the circuit given. Now I want you to implement this particular function, so you modify the circuit. Okay.
Okay.
There will be some questions which are direct, but largely indirect questions.
And syllabus for COA will be till next week.
Syllabus for COA will be till next week. I mean to say that one more class syllabus for COA will be next week. Next week means we have, let me check the timetable. We have classes on 10th. Last class is on 10th. Your mid semester starts from 13th, na?
Yes, sir.
But 10th is a mid semester break or it's a class day? Is there any mid-sem break? I mean to say that mid-sem preparatory day, is it there, something like that? If not, then 10th will be the last class. Okay, but probably I will freeze the syllabus after Friday's class. Probably I will freeze the syllabus for mid-sem after Friday's class, so that you do not need to worry about next week's class. Okay.
Yes, sir.
ठीक है, चलो, done.
Yes, sir.